Welcome to the second part of lecture 2. In the first part of lecture 2 we saw how to solve non-homogeneous ODEs. We saw that the solution of non-homogeneous ODEs is given by the sum of the complementary function, which is the solution of the homogeneous counterpart, plus the particular integral. The particular integral takes the form of the forcing function ft and its derivatives. In this lecture, we are going to see how to solve integral differential equations in which you have an integral term, and we're also going to see how to solve simultaneous differential equations, simultaneous ODEs. That means a set of ODEs. Now let us take this up quickly. So integral differential equations are very simple. They have an integral term, so to convert them into an ODE in the standard form, we just need to differentiate the whole equation first. For example, you have, let us suppose, a differential equation which is given like this. Which has terms up to a naught xt, but it also has an integral term after that, which is, say for example, something like this, integral of x tau d tau, and then you have a forcing function on the right hand side. So the easiest way to solve this is to differentiate the whole thing once and rewrite it as an ordinary differential equation. So when you differentiate the whole thing once, you will get the first term would be an xn plus 1t, plus the second term would be an minus 1 xnt, plus you will go up to a0. This will be the first differential now, x dash t, and this will be xt, and on the right hand side you'll have f dash t. So this is transformed into an ordinary differential equation, a standard format of the ordinary differential equation. This is one way of solving it. The other way of solving it is to make a change of variables. Change of variables would be something like, let us suppose that y dash t is equal to xt. Then you rewrite the original equation in terms of y dash t rewrite the original equation in terms of yt. So the first term, when y dash t is xt, that means you can differentiate this n times. So xnt would be yn plus 1t. So you have an yn plus 1t plus an minus 1 ynt plus, we'll go up to a0 y dash t plus a minus 1 yt is equal to, the right hand remains the same, ft. Please note that here the right hand changes, it becomes f dash t. Here it remains the same, it is ft. Then you can solve this equation, and the solution that you get yt, you will then differentiate the solution to give you xt. So this is how you solve integral differential equation. It consists of an additional step in which you change the differential equation, the integral differential equation, into an ODE in standard format, either by a change of variables or by differentiating once throughout. The other thing that we're interested in right now is a set of simultaneous differential equations. What does this mean? Simultaneous differential equations. You'll have more than one equation and more than one variables. Like for example, you have something like this. You're writing, you have two variables x and y, alpha 1 x dash t plus alpha 0 xt plus beta 1 y dash t plus beta 0 yt is equal to 0, and then alpha 2 x dash t plus alpha, say for example alpha 3 xt plus beta 2 y dash t plus beta 3 yt is equal to 0. So you have a set of two differential equations, equation number 1, equation number 2, and you don't have just one unknown, one variable xt, you also have another variable which is yt. So this is a set of simultaneous ordinary differential equations with constant coefficients which is homogeneous. So again, the way to solve this is similar. You're going to assume a specific form. Let us say xt is given by c1 e to the power pt, and yt has a form given by c2 e to the power pt, and let us substitute these two in the original set of equations that we have. So what do we get? You'll get alpha 1 p c1 e to the power pt plus alpha 0 c1 e to the power pt plus beta 1. Now differentiate this, p c2 e to the power pt plus beta 0 c2 e to the power pt is equal to 0. This is for the first equation. So you can write c1 e to the power pt alpha 1 p plus alpha 0, and then c2 e to the power pt beta 1 p plus beta 0 is equal to 0. This is the first equation. The second equation would be similar. You can write it by inspection. c1 e to the power pt will come out, so you'll have alpha 2p plus alpha 3, and then c2 e to the power pt will come out. You'll have beta 2p plus beta 3 equal to 0. So these two equations you get when you substitute the solution that you have assumed into the original set of equations. This you can write down in matrix form like this. You can write down it like this: alpha 1p plus alpha 0, beta 1p plus beta 0, and then alpha 2p plus alpha 3, and beta 2p plus beta 3 times c1 e to the power pt c2 e to the power pt is equal to 0 0, right? So this is just the product of two matrices. It gives you two equations. Now the non-trivial solution in this case is of course going to be when the determinant of this matrix on the left hand side, the first matrix, is 0, because you have a trivial solution when p is minus infinity, but we're not interested in that. So when you see this equation and you try to solve it, you'll get a solution for the determinant of this thing. For the determinant of alpha 1p plus alpha 0, beta 1p plus beta 0, alpha 2p plus alpha 3, beta 2p plus beta 3, the determinant equal to 0. This is the characteristic equation. The determinant equal to 0 is the characteristic equation for the set of simultaneous differential equations. It will be a quadratic equation. It will be a quadratic equation because you're getting powers of p. So power 1 of p and power 1 of p be getting multiplied. Okay, quadratic equation, so you'll have two roots, p is equal to p1 and p2, and then you can put in these two roots in the solution that you have assumed to give you the two variables. So your xt will be c1 e to the power p1t plus c2 e to the power p2t, and your yt is going to be c3 e to the power p1t plus c4 e to the power p2t, and this is going to be your solution to the question. So let us take a simple question, and let us try to solve it and see whether we can solve the set of simultaneous differential equations. These are important in network analysis because we get these kind of equations when we try to solve circuits which have mutual inductance like transformers. So that's why we're studying them. So let us suppose you have a set of simultaneous differential equations which is given by suppose we are given the set of simultaneous differential equations twice x dash t plus 4xt plus yt minus y dash t minus yt is equal to 0. Then x dash t plus 2xt plus y dash t plus yt is equal to 0. So the characteristic equation can obtain simply by substituting for p here. So this is going to be 2p plus 4 and p minus 1. The characteristic equation is this is p plus 2, this is p plus 1. The characteristic equation is given by this determinant equal to 0. If you solve this, you'll get p is equal to minus 2 minus 3. So the solution is xt is equal to c1 e to the power minus 2t plus c2 e to the power minus 3t, and yt equal to c3 e to the power minus 2t plus c4 e to the power minus 3t. Then you can find out the values of c1, c2, c3 and c4 by additional information given about the differential equations. You in this case need the values of x at 0 plus, x dash at 0 plus, and the value of y at 0 plus and y dash at 0 plus. So these four values, put them in here and you solve the homogeneous differential equation. I can have a slight modification. Suppose instead of This being homogeneous, you have some forcing function. Let us suppose you have a forcing function here which is given by say some 4 e to the power 5t. Now how do you solve this? This is the complementary function. Okay, this is not the complete solution, so this is xct, this is yct. You'll have to see what is the particular integral for x and what is the particular integral for y. So the particular integral for x is going to take this form, right? So it will be some a e to the power 5t, and similarly the particular integral for y will also take this form, so it will be some b e to the power 5t. So the complete solution would be x is equal to xct plus xpt, where x is given by this equation and xp is given by this equation, and similarly y is equal to yct given by this equation plus ypt given by this equation. So this is let me write xt and yt. So this is the complete solution, and to evaluate a and b, you put them in the original equation because these are particular solutions to this set of equations and they are valid without the complementary function also. So if you do that, you'll get the values of a and b. Like for example, if I do it here, I can put in 2, the say a first differential of xpt, that is 2 into 5a e to the power 5t plus 4a e to the power 5t plus y dash, that is b e to the power 5t minus yt. Y dash also y dash will have a 5 here, right? Minus b e to the power 5t is equal to 4 e to the power 5t. So this gives me the first equation, which is 10a plus 4a plus 5b minus b is equal to 4, which is 14a minus 4b is equal to 4. So this is the first equation that I get when I substitute the particular integral here, and I'll also get a similar equation if I substitute the particular integral in here. So I get two equations for a and b. This gives me the solution for a, this gives me the solution for b, right? And then I put in the initial conditions and they'll tell me about c1, c2, c3 and c4, and finally the problem is solved. So try this problem and try to see what is your answer. So this is how you do simultaneous differential equations. So in a nutshell, we have seen in these two lectures, lecture 1 and lecture 2, that the governing equations of networks that we are going to solve, specific types of networks which cover, of course, a large domain of the networks that are studied or made or synthesized or analyzed. So we have seen that the governing equations are differential equations and they have a particular form. They are ordinary differential equations, and we have seen that ordinary differential equations can be solved very easily using the concepts that we have learned in mathematics. So we saw how to solve homogeneous ordinary differential equations, we saw how to solve non-homogeneous ordinary differential equations, and we saw how to solve integral differential equations, right? Integral differential equations, and we also saw how to solve simultaneous ODEs. So with this information, we should be able to solve some simple circuits, and slowly we'll move on to more complicated ones. Like for example, if we are given a simple circuit like this, source, a resistance, and an inductance. Suppose it is given that this is 5 volts, this is 2 ohms, this is 3 Henry, or some you want to find the current in the circuit. So you can write 5 is equal to 2I, where this is the current IT, plus 3 dit by dt. And suppose you're given the initial conditions that I0 is 0, or to be more precise, I0 plus is 0. So this, you see, is a non-homogeneous differential equation. You'll have two parts, the complementary function, the particular integral. So the complementary function is going to be 3p plus 2 is equal to 0. So p is minus 2 by 3. So this is the characteristic equation, sorry. So the complementary function is going to be c e to the power minus 2 by 3t. The particular integral is going to be a constant. We saw this before. It's going to be some a. This is going to satisfy this equation. So when you put this xpt, you put it is equal to xpt is equal to a in the original equation, in star, you should be able to satisfy it. So you'll get 2 is equal to 5 is equal to twice a plus 3 into differential of a, which is 0. So a is 5 by 2. So your solution is it is going to be the complementary function plus the particular integral, which is c e to the power minus 2 by 3t plus a, which is 5 by 2. And then you put in your initial condition, which is I0 plus is 0, which means that c plus 5 by 2 is 0, which gives you c is equal to minus 5 by 2, and this gives you it is equal to 5 by 2 1 minus e to the power minus 2 by 3t. So this tells you how the current in the inductor is going to change with respect to time, right? And we can plot this graph, and you must have seen this graph before. This is your current, this is your time, and this is negative exponential. So if you want to plot e to the power minus x, e to the power minus x would be something like this, e to the power minus t, and 1 minus e to the power minus t is going to be something like this. So 1 minus this is going to be something like this. That's what we are doing. We have to plot 1 minus e to the power minus 3t. So it is going to have a shape which is going to be something like this, right? And it's going to fix, it's going to be a straight line after some time, and this is how the current is going to rise. It's going to start from 0, and then it is going to become, after some time, it's going to become, because at t is equal to infinity, you see the value is 5 by 2, so it's going to stabilize at 5 by 2 amperes. And that's what you expect, because the resistance is 2 and it's a DC circuit. So after some time the inductance will behave like a short circuit, and the current, steady state current in this circuit is going to be 5 by 2 amperes. So this is how you use differential equations to solve this problem in network analysis. In the subsequent lectures we'll see all of this in more detail. Thank you very much.